In this unit, we'll consider one of the applications of derivatives that are near and dear to the heart of every student of calculus, the study of optimization. We're going to springboard our work in optimization by looking at critical points again, topic from last week, and formalizing ways to classify them. In particular, we're going to be interested in whether a particular critical point is a minimum, a maximum, or neither. The reason for this is we don't always want to have to sketch a graph to determine if the point, the critical point we found, is the best point in some sense for the function we're looking at, or the worst point in some sense, the difference between a minimum and a maximum. One of the methods for determining the type of a critical point is the first derivative test. We'll also be looking at the second derivative test in a moment, if you're more familiar with that. So the first derivative test is a method to classify critical points, and the way it works is we look at what happens in the lead up to the function and after, or the lead up to the critical point, and then what happens afterwards, after we leave a critical point. If there's a local minimum at some point C, then the critical point in the middle here would be a minimum if that was our sketch. And what we notice is that the derivative would be negative if we were coming in from the left and we're reaching a minimum because the function is decreasing. And on the right, or as x increases, we would have positive slopes. That combination is going to give us a local minimum. Likewise, a local maximum is going to have positive slopes in the lead up towards the critical point, and it's going to have negative slopes, decreasing values, as we escape the critical point, or as we move right from the critical point. And the other possibilities really are only positive, positive, and negative, negative. We can split those up. This would be a function where the function's increasing, briefly has slope of 0, and then continues on, or the opposite scenario where the function's always decreasing, briefly has a slope of 0, and then continues on decreasing. This gets us back to our issue of points of inflection. This critical point would be a point of inflection, but not every point of inflection needs to be a critical point. This point is a point of inflection between concave down and concave up, but it's definitely not a critical point. All right, let's erase that. So the first derivative test, lets us test what kind of critical point we have by looking at the slope on either side of a critical point. Let's put it to the test. Let's look at the function, this cubic function, 2x cubed minus 9x squared plus 12x plus 3. Use the first derivative test to determine what the type of the critical points are. All right. First goal then is to find the critical points. And to do that, we need the derivative, of course, and the derivative is just a polynomial, so it's pretty straightforward here. Differentiate, we get those. Let's make that a little more clear, so plus 12 at the end. And we're going to set that equal to 0, and we note f prime is defined everywhere. And under those conditions, we don't need to worry about critical points, which are cusps. We only need to worry about critical points where the derivative is 0. So we'll do that. We'll set our critical derivative here, our derivative equal to 0, and solve for x. And when we solve for x here, we notice we can divide through by 6. And that gives us some nice factors, x minus 2 and x minus 1. So x equals 2 and 1 are the critical points. Of our function f of x. All right, so we've identified the critical points now. Our next challenge is to identify their type. Are they local mins, local maxes? What's happening there? Well, I find the easiest way to do this is to sketch out a sign chart where we look at the sign of f prime. We know that at the points x equals 1 and x equals 2, the value of the sign is going to be 0 for the sign of f prime. Let's try to keep this coloring consistent here. So all the green markings will be about the sign of f prime. And the x values are in here, are blue here. You can do test values, you can sub in, you can imagine subbing in values, whatever you like. I think it's pretty clear from this structure here, sorry, I lost an x, there we go. I think it's pretty clear from this structure here that if x is really big, this whole thing's going to be positive. If we go back up to the original derivative, it's equally clear. When x squared gets big, the whole thing gets positive. When x is big and negative, down at this end of things, then we have large negative numbers squared, those become positive. And in between, when x is between 2 and bigger than 1, we're going to get a negative and a positive. We're going to get a negative overall in between. What that means when we add a sketch of our function, we could go straight to the first derivative test if we liked, but I like drawing it out just for clarity. If the sign of the derivative is positive, the function's increasing, hits a 0 slope, and then is decreasing, hits a 0 slope, and then is increasing again, then that would be the sketch of our function. And so we would conclude by the first derivative test that our point at x equals 1 is a local maximum. The function's going up and up and up, and then reaching that point. And the point x equals 2 is a local minimum for the function. So analyzing the first derivative information lets us know what's happening just before, just after the critical points, and then to classify them as min, max, or neither. Now, can we extend what we just learned to identify the number of real solutions to this equation? So this question has nothing on the surface to do with critical points. However, we just found some important information about the shape of this graph through the critical points. Now, how are we going to take advantage of that? Well, we know the graph looks something like this. What can we do to put that together with the points, the landmark points at x equals 1 and x equals 2? Well, we can actually find the function value there, and that'll tell us where on these axes this graph lies. So at f of 1 is 2 minus 9 plus 12 plus 3. And that's better known as 15, 6, that's better known as 8. And f of 2 will be 2 times 8 minus 9 times 4 plus 12 times 2 plus 3. And if we sort all that out, 36, so we're down 12, we're up 4, we're up 3, it's up 7. So that tells us that our points, the critical points we identified earlier, are at 8 and then at 7. And with the shape of a cubic, and knowing that this is a local max, then a local min, we can determine that there's only one possible solution where this graph crosses the x-axis. The only root or only possible solution to that equation. We can write it either way. Oops, it's a root, not a roof. Only root of f of x, or the only solution to f of x equals 0. If we had a different function, maybe with a different vertical scaling, imagine we had minus 12 or something here, we could move this whole graph down, and we might have had something like this, where the graph crosses 3 times for a cubic. That's very possible. However, for this particular function, we can confidently say that there's only one solution because of the structure of the min-max and the fact that it's a cubic that then heads off to infinity and never comes back down again, and it goes off towards negative infinity and never comes back up again on this side. All right, So that's the first derivative test in action and what we can learn from it. Let's take a quick look at the second derivative test. Unsurprisingly, the first derivative test uses the first derivative. Here's the fine print, though. This is what's important. It uses the first derivative around the critical point. Now, why does that make sense? Well, because f prime at the point is always 0 or undefined. So we couldn't use the derivative at the point to give us any information at all. We already know or have used that information to identify it as a critical point. The second derivative test does use the second derivative, thus its name, and importantly, as a difference, it uses the second derivative at the critical point to evaluate it. So here's our testing thing. So if the derivative is 0, notice it can't be undefined here because we can't differentiate if the first derivative is undefined. So if it is a critical point with the derivative equal to 0 and the second derivative is positive, which means concave up, well then we have the shape, local minimum. We have a point with 0 derivative and the shape is concave up, it must be a local minimum. If the second derivative is negative, we know the function is concave down, and the critical point in that interval then must be a local maximum. Now the slightly frustrating part is if the second derivative equals 0, then the test is inconclusive. And I can show you a couple examples here. If y is equal to x cubed, the function will look like x cubed, and it's neither min nor max. And the second derivative is 0 for that. Likewise, we get another 0 second derivative if we had y equals x to the power 4. And that's our almost parabolic shape, same kind of bowl shape anyway. And this is the critical point at 0 there is a local min. But in both those cases, the second derivative, you can check it yourself, would just be x to some power. The second derivative, when we plug in x equals 0, is going to give us 0 in both these scenarios. In other words, we can't tell. So the second derivative is great when you get a non-zero second derivative. It's inconclusive when we get a second derivative of 0. And that's why some people prefer the first derivative test, if at all possible, because it always tells you what kind of critical point you have. There's no ambiguity with it. There's a possible ambiguity with the second derivative test. Let's take a look at this function here then. Notice we've been given not the function, but its derivative already. So we're saving you a step here. The derivative of some function is cos x squared plus 2x minus 1. What kind of critical point does it have at x equals 0? Let's just check that x equals 0 is a critical point. How do we do that? We plug in x equals 0 into the derivative, which is what we have, and see what we get. F prime of 0 is cos of 0 plus 2 times 0 minus 1. That's 1 minus 1, that is 0. F prime of x equals 0 at x equals 0. Okay, so we're dealing with a critical point. The next thing is let's take our second derivative here and see what it does. Because the first derivative, imagine the signs around here. It'll be pretty complicated. We're going to try to use the second derivative test. For that, we of course need the second derivative. And the second derivative will be negative sine of x squared times chain rule times the 2x derivative of the inside plus 2. At the point x equals 0, what's the concavity? So we know there's a flat point at 0. What's the concavity there? We plug in x equals 0 into our second derivative. We're going to get negative sine of 0 times 0 plus 2. That's 2. That's positive, which means that the original function is concave up at x equals 0. And that means the shape concave up is like that. So our critical point at x equals 0 must be a local minimum. So by the second derivative test, x equals 0 is a local minimum of our function f of x.